Hi, my name is Tommy Sebastian. I'm a member of the senior technical staff at MIT Lincoln Laboratory, and today I'm going to talk to you about the toroidal propeller.
Traditional propellers have remained mostly unchanged since the Wright brothers' first manned flight in 1903. Toroidal propellers are a recent innovation in propeller technology. These devices are ring-shaped, with blades looping around one another. We have seen some articles and videos that have hyped them up, but how revolutionary are they really? Propellers are meant to collect fluid, often air or water, and push it through using a rotating motion. They are evolutions of the Archimedes screw, which was likely utilised in ancient Egypt hundreds of years before the Archimedes described it in 234 BCE. These devices are designed to revolve, and there have been few revolutionary design changes in a long time, like the prop-driven aircraft, which still uses twisted aerofoil blade props, similar in design to the bamboo copters Chinese children were enjoying 2,400 years ago. These props have surprisingly small gains in efficiency over the wooden props the Wright brothers developed in wind tunnels in 1903. Screw-style propellers, some dating back to 1700s, are still used on boats today. As engineers learn more about aerodynamics and conduct new tests, propeller designs are becoming increasingly complicated. These include numerous blades, high sweep angles, blade tip devices, and other characteristics to improve performance in various circumstances. So we're intrigued to discover a couple of people who have demonstrated significant advancements in both air and water using a markedly different shape. Specifically, strange twisted loop shapes that appear not only to be much quieter than traditional designs, but also so much more efficient, particularly in the marine space, that they could represent a profound leap. In 2017, MIT researchers submitted a patent for toroidal propellers. Their patent establishes that this device is more efficient and quieter than ordinary propellers. An MIT revelation last year that toroidal propellers had won one of the MIT Lincoln's Laboratory's 2022 R&D 100 awards sparked much interest. There has been much testing with 3D printed toroidal propellers, but not all of them have turned out well. Propellers, as we know, are pretty loud, says Dr. Sebastian, a senior member of the Lincoln Lab's Structural and Thermal Fluids Engineering Group. And we can examine wings to discover how that works. When designers were coming up with insane ideas for aeroplanes in the early 1900s and throughout World War II, there were a couple of concepts that looked like these ring wings. So I was wondering what it might look like to make a ring wing into a propeller. We came up with an initial concept of using a toroidal shape, this angular wing shape, to hopefully make a quieter propeller, Sebastian continued. We had an intern of mine who was just phenomenal and ran with the idea. He took the concept and created a bunch of iterations using 3D printers. After a few tries, the team discovered a good design that lowered noise levels at a given thrust level and noise in the 1 to 5 kHz band. Indeed, they sounded more like a rushing breeze than a propeller, generating a far less invasive noise. According to scientists, a drone running these propellers produced nearly the same level of noise as a standard drone at twice the distance. Coincidentally, in 2012, a US engineer firm called Sharrow Marine also created a toroidal propeller for boats, which proved to be more efficient and quieter than typical marine propellers. Sharrow Marine has achieved quite outstanding results with their boat propellers that employ loops instead of regular blades. After several years of development, the business has tested its props against hundreds of ordinary propellers, and the results are outstanding. Sharrow props simply do not generate tip vortices, which are major causes of energy loss and a surprisingly big component of an outboard engine's total noise. How is this futuristic marvel designed? Toroidal propellers are propellers that are much quieter than normal ones due to their complicated structure, which reduces the power of the vortex that occurs naturally around the propeller's blade tips. This occurs because there is a high pressure zone underneath the blade and low pressure zone above it. As high pressure air goes from beneath the blade to the low pressure zone above it, it forms a spiral, a vortex, which is just a swirling flow of air, water, or any other fluid. This vortex effect is not limited to just propeller blades, which are basically revolving wings. It may also be observed on a plane's wing. Engineers have conducted extensive studies on wingtip devices that could mitigate this. However, there are methods for decreasing tip vortices, such as utilising closed-loop structures, such as those seen in the toroidal propellers. Even though the fundamental propeller form has remained unchanged since its inception, other propeller blade shapes have been proposed. Engineers must perform design trade-off analysis to test these. Some of these methods have been tried to make helicopter blades and drones more efficient and quieter. Propeller noise can be reduced by putting rings of acoustic treatment around the periphery of a prop's root, which can also serve as a prop guard for safety. However, these act as a parasitic mass, lowering battery life and catching the wind in outdoor circumstances, making the drone work more to maintain stability. The researchers had already examined these strange-looking toroidal props to see whether these might be a thrust-efficient penalty. Apparently not, as the team's best-performing B160 design was not only quieter at a given thrust level than the best standard propeller they tested, but also produced more thrust at a given power. This is pretty impressive, given that standard propellers have more than a century of development behind them, and these toroids are still in their early years with much more optimization to come. It is imperative to realise that propeller geometry must be optimised for a given operational envelope. This includes the parameters of the fluid or air in which it functions, as well as the rotation and forward speeds. Outside of this envelope, the propeller will function badly. No one has yet developed a magical propeller shape that produces low noise and great efficiency across all operating situations and sizes. Toroidal propellers are no exception. Based on the little data available, their advantages have yet to be adequately assessed. A well-designed toroidal propeller will perform far better than a badly built regular propeller, but the comparison is not fair. Toroidal propellers may provide benefits in certain operating situations, such as thick fluids or a specific speed range. However, it is unclear how a toroidal propeller compares to a well-designed, classical propeller under the same conditions, and research is ongoing to better understand them. This is difficult because improvements are always relative to a benchmark, which may not be the most efficient design to begin with. Another point of comparison that does not appear to have been reported for toroidal propellers is the comparison of various propellers with the same thrust. Only then can you observe the actual benefits of noise reduction and the energy required to spin the propeller. Previous optimization studies, such as employing machine learning approaches to determine appropriate geometries, were done successfully. Engineers are also attempting to create propellers that generate less noise by considering how humans perceive sound. Their loop design not only increases structural stability, but also reduces the possibility of a prop cutting, slipping or snagging on anything it comes into contact with. It won't make the propeller hitting you in the face enjoyable still, but there's definitely still a slight safety gain. What is keeping us from upgrading all current propellers then? These toroidal propellers also have significant downsides. They are highly intricate shapes, making them far more difficult to manufacture than ordinary propellers, made using cheap and simple injection moulding. They are probably something that should have been 3D printed. Even if they're double or triple the cost of propellers, they are a low-cost component of a drone, and the typical impact may not be too severe on the wallet. It's uncertain at this point if the ideas like these may be useful on a bigger scale, even replacing traditional propellers on fixed-wing aircrafts, or even electric VTOL air taxis. The latter looks to be substantially quieter than helicopters, but if they wind up overwhelming the urban sky with rapid, inexpensive, green aerial transport, every decibel of noise will matter when it comes to public and regulatory opposition. The key concerns are what frequencies those big props will occupy in the audio spectrum, and whether the toroidal props will convert the sound to a more human-friendly range. The complicated propeller design requires special care to reduce unwanted vibrations, which pose a significant risk at high spinning speeds. This leads to higher production costs. When using toroidal propellers for drones, the increased weight influences the drone's responsiveness and stability. This is especially critical while operating in windy or turbulent conditions, such as severe weather. These toroidal propellers are an exciting development in propeller design, at least in some cases. While they can be quieter, they won't completely replace traditional props just yet. There's no single propeller design that will suit all situations. If you did like this video, make sure to check out our other videos. Feel free to subscribe for more intriguing content. And please do let us know if you found the video useful, and we'll see you in the next one.